So good morning students. Today I'm starting the new topic which is on Lyapunov stability theory. So far what you have learned? So far you have learned the details of state space analysis, the details of phase plane analysis, and after covering these two topics I am now starting this topic on Lyapunov stability theory. There is a reason for this because I can easily start this topic first, then I can go to phase analysis, then I can go to state space analysis. No, I didn't want this. I wanted to start this chapter after explaining and discussing on state space theory at first, and then phase plane analysis secondly. Reason is why? Because the learning is should be sequential. First of all, you have understood that what is state variable and how to represent any system, whether it is physical or mathematical differential equation or transfer function, how to represent this in terms of state variable, and how to obtain the ABCD matrix. And you also have learned that how to choose the physical state variables such as for RLC series circuit, capacitor voltage and inductor current are the state variables, and for mass spring damper system, the displacement and the velocity are the state variables. And for what is the reason for choosing these state variables, due to the reason for storing the energy in the components. So these are the concept now you already have. And then in case of phase plane analysis, what you have learned that how to draw the phase plane trajectory if any differential equation given to you, whether it is linear or non-linear. And you know that to draw the phase plane trajectory, after drawing, you already also have learned that, I hope that after drawing the phase plane trajectory, from the nature of the phase plane trajectory around the equilibrium point, the stability can be concluded. And you always remember that phase plane trajectory is drawn in the phase plane along with the phase plane is constructed along considering x axis as x1 and y axis as x2. And to draw the phase plane trajectory, you need to have a initial point in the phase plane, anywhere in the phase plane, right? Now after considering the initial point on the phase plane, your trajectory will start moving according to the dynamics of linear or nonlinear dynamics of the equation given to you, of course differential equation, which must be second order. And whether is it converging or diverging around the equilibrium point or not, you have to check, and from that point of view you can conclude the stability of the linear or nonlinear system. So one point is clear, that the trajectory will start from phase plane trajectory will start from the initial point, and it may go to equilibrium point or may not go to equilibrium point depending on the differential equation and the types of the differential equations, right? Now then after we are moving to this topic which is Lyapunov stability theory. And let me tell you that Lyapunov stability theory is used to determine the stability of the system. Now, you already learned that from the previous semester, Control System 1, that stability can be determined using various techniques. You know that Routh technique, which is used to find out the stability, and Root-Lucas technique is also is also used to determine the stability, Bode plot, Nyquist plot, etc. Now these in the last semester you have learned about the linear system. So these are the techniques which are used to determine the stability of the linear system. Now there are various methods, you have various options in your hand to find out the stability of the linear system. But actually in literature, to determine the stability of the nonlinear system, very few methods are available. One of them is phase plane analysis, which we have already learned. But phase plane trajectory, one limitation of phase plane analysis is that it is applicable to second order system, because the phase plane is constructed by considering x1 and x2. Lyapunov stability theory is also uh, used to find out the stability, but it requires the concept of energy. And one point is to be noted that the methods which are used to find out the stability of the nonlinear system can be used to determine the stability of the linear system very efficiently. That's why we used to we use the phase plane analysis for determining the stability of the nonlinear and linear system. I had shown some example on this. Similarly, Lyapunov stability theory can be applied to linear as well as nonlinear system. But for linear system, we have various options. But that's why Lyapunov stability theory is meant to be applied for determining the stability of the nonlinear system. Now, let me tell you that the Lyapunov stability theory, now, like in case of previous semester, for frequency response, both the plot, Nyquist plot, these techniques are basically based on frequency response concept, and Root-Logas technique, Routh's technique is based on basically time response concepts, like phase plane trajectory, determining the stability using phase plane trajectory is based on the concept of equilibrium point and or singular point. And I discussed about various types of singularity so far in my last video. Now, Lyapunov stability theory is also based on a new concept. Concept is the basis of energy. Now, energy, whenever I talk about energy, you must be uh, uh, familiar with this term energy when you studied the state space analysis. Can you remember? Say for RLC series circuit, we generally select the capacitor voltage and inductor current as state variables, because capacitor can also store the energy in terms of half CV square. Now half and C is constant, so Vc is the capacitor voltage, so Vc is responsible for storing the energy in the capacitor. That's why Vc, voltage across the capacitor, is one of the state variable, because it is a variable which is responsible for storing the energy in the capacitor as well as in the circuit, because capacitor is included in the series RLC circuit. Similarly, for storing the energy in the inductor, the formula is used for is used as half Li square, where half and L is constant, so IL is the variable. So IL is the inductor current, which is the variable. In this case, it is also state variable because it is also responsible for storing the energy in the inductor. And since inductor and capacitors are however, there is a resistor, but there is no variable to store the energy in the resistor always dissipates energy. That's why inductor current and capacitor voltage are basically chosen as state variable, because they are the energy variable for storing the energy in the system. So again, I'm telling right now that the Lyapunov stability theory is based on the energy. So there must be a relation between this concept of state space analysis and the concept of Lyapunov stability theory, because they also requires selection of state variables also requires the concept of energy, and the stability based on Lyapunov's theory, it also requires the concept of energy. Now, before I start in detail regarding Lyapunov stability theory, let me tell you another concept, which is asymptotic stability, because when I start this Lyapunov stability theory in detail, I often try to bring the word asymptotic stability. Now, what is asymptotic stability? However, asymptotic stability, I will explain asymptotic stability, the concept of asymptotic stability in detail at the last video of my this stability Lyapunov stability theory lecture. However, before I start concept, before I bring the concept of energy to explain the Lyapunov stability theory, let me tell you in short, in very short, about asymptotic stability. I'm just giving you a very small introduction regarding asymptotic stability. Consider an RLC series circuit. Okay, just imagine. I'm not going to draw this RLC series circuit. You can imagine it. Okay, consider the RLC series circuit with capacitor initially charged to some voltage. You understand? And this initial voltage is sufficient to operate the system, I mean RLC circuit, without any external input. This initial voltage drives the current till the capacitor gets fully discharged. Now imagine there is a RLC series circuit. Oh, let me. Okay, for your convenience, I'm drawing this diagram. I'm just discussing on asymptotic stability. However, I will discuss in detail about asymptotic stability in the large, asymptotic stability in the small, asymptotic stability in the sense of Lyapunov. Before that, I'm just giving you a very small introduction regarding from practical point of view, that what is actually what is asymptotic stability is meant for. So let me draw the circuit. What I am telling that is a series RLC circuit. Okay, the circuit is closed completely, right? And there is no input voltage at the input terminal. So will there be any current? We have not applied any external input from the outside to the circuit. So how the current will flow? Is it possible to flow the current? Yes, if it is possible, then if you bring your a charged capacitor, say initially for a charged capacitor, there should be a voltage across the capacitor. Now this voltage is now actually supply the current in the circuit. Okay, now how long this current will flow across this circuit? How long? Because you know there is a resistor present in this circuit, so the resistor will dissipate the energy. So whatever your energy stored in the capacitor must be discharged, must be dissipated across the resistor. So and there is no constant voltage or constant source which is applied from outside. So the voltage developed by the capacitor for storage because of the stored energy will now drive the current, and the current will flow as long as the resistor dissipates the energy. But after some time, I'm bringing the word time, time, right? After some time, the current will, there should be no current, because ultimately the resistor will dissipate the energy. So what type of system it is? It is a forced system or unforced system? What do you say? It is a unforced system. An unforced system means there is no external input or external force applied. So there is no external input in this case, so it is a case of unforced system. But the circuit is driven by the capacitor voltage, and capacitor voltage we may consider as initial condition VC may also say VC is we generally VC we assume, which is one of the state variable x1, and so another state variable is, say, if it is IL, which is x2. So x1 VC, suppose initially, say, inductor, there is no stored energy in the inductor, but only the storing of energy is done by the capacitor. So only capacitor will drive the circuit. So I can assume that initially, okay, initially x2 is 0, but suppose x1 has some value, say 5 volt, maybe. Now, what does it mean? This is a on what I am going to direct my point. My point is that this is a circuit which is a case of unforced system, since there is no input applied externally, and the circuit is driven by the capacitor voltage, and capacitor voltage is one of the state variable, and it has some initial value which is a 5 volt in this case. So on the phase plane, the phase plane is constructed by considering x1. Now x1, we assume x1 as Vc, and x2 is IL. So if I consider this initial condition, that x2 is 0 and x1 is 5, then 5 0 means maybe that point is my initial point. So your trajectory will start from that point. I don't know where it will go. You have to find out the equilibrium point. After applying KVL, you have to find out the differential equation. Then, as you know that you have to determine the expression for slope of the trajectory, and from the slope of the trajectory you have to check that for which values of x1 and x2 the slope becomes indeterminate, and that will be the equilibrium point. And in this case I know that origin should be a equilibrium point. So it may that the trajectory may converge to it, or may not converge. It depends on the differential equation coming out of this circuit. Okay, but what I want to say, I want to just let you know that asymptotic stability, I'm not going to define the asymptotic stability now. I'm going to just to let you know that asymptotic stability is the case of determining stability for such cases. Now, what is this case? What is that case? This is an unforced system. Remember the unforced system, but this system is driven by the initial condition. This system is driven without any initial condition. There is no possibility of the functioning of the circuit, and there is no without any initial condition there is no case of understanding any trajectory on the phase plane. So asymptotic stability, my point, I'm repeating my point again and again, uh, that asymptotic stability is the case. What is the case? Asymptotic stability is applicable for which cases? My answer is asymptotic stability is the case of determining the stability for the unforced system where the system is driven by the initial condition. That's it. So that's why asymptotic stability is sometimes also known as zero input stability. I mean, there is no input, that's why it is a zero input stability. Without any external input, or due to only initial condition, that you have to find out if the system is stable or not. That's it. That is the case of asymptotic stability, what I want to explain before I proceed to Lyapunov stability theory. Another important, that's the first point I explained to you. Another important point is that why sometimes this is my observation, and that I'm sharing my observation with you, so that you can, when I start my Lyapunov stability theory, you can relate this observation with the importance of Lyapunov stability theory. Actually, you can see, if whatever your trajectory, what is this trajectory? Basically, this trajectory is basically graphical solution of the differential equation. You already know it. I elaborately explained this in my previous videos, that phase plane trajectory is nothing but the graphical solution of the differential equation. Phase plane trajectory is graphical solution of differential equation. So one thing is very clear to you, that once the phase plane trajectory is drawn, we can determine the stability around the equilibrium point. by observing the converging and diverging characteristics of the trajectory around the equilibrium point. But trajectory must be drawn, right? Trajectory is nothing but the graphical solution of the differential equation. So we are basically interested, if I say that we are interested in drawing the phase plane trajectory, that means that we are actually interested in plotting the solution of the differential equation. Remember, we are discussing about the importance of phase plane trajectory, but actually phase plane trajectory is nothing but the graphical solution of the differential equation. So basically we are interested in solution of differential equation to have some pictorial view on the plane. We are drawing this to have graphical solution, but this is basically a solution, right? This is basically we are working on the solution of the differential equation. Now solution of differential equation is possible mathematically as well. Graphical solution will give you the converging and diverging characteristics, and it will give you a pictorial view of the convergent and divergent characteristics. That's why you can easily conclude the stability on the stability. But if you are able to draw the if you are able to have the differential equation mathematically, you can also find out the stability. Problem is that for linear differential equation there is no problem, but for non-linear differential equation, so if getting an explicit solution of is not so easy task, because ultimately another point is that time, because ultimately it will take some time to conclude that the system will converge or diverge. The trajectory has to move. Okay, the trajectory has to move means it will take some time for the movement. So actually we are basically interested uh, uh, to see that what will happen uh, at last when time tends to infinity. So basically we are interested to know that solution of what will happen to solution of the differential equation when time tends to infinity. That's why you are observing graphically on the phase plane, but actually we are trying to observe that what will happen to the solution of the differential equation when time tends to infinity. And uh, this actually from this point I want to uh, say that as I have said to you already, that Lyapunov stability theory is based on energy. So energy, what will happen to energy when time tends to infinity? What will happen to energy of the system? Say if I consider this system, I will show you I will take one example and I will explain in detail. Say I'm taking this example of RLC series circuit. What will happen to the total energy? Because total energy depends on the inductor energy as well as capacity energy, and this is unforced system, so there is no source of external energy. So the energy is given by the capacitor and an inductor due to the initial condition. So what will happen to the energy when time tends to infinity? So again, coming back to the point, my asymptotic stability is the case for unforced system. Asymptotic stability, I'm hammering on this point again and again. Asymptotic stability is the case for unforced system. Okay, what will happen to energy of the system when time tends to infinity? That is about Lyapunov stability theory in short. That is the background of Lyapunov stability theory. What will happen to energy when time tends to infinity? Because when time from the initial time, from the initial condition from the initial time, say the this initial condition is the value of x20 and x1 equals to 5 at time t0. So when from the time t0, this time 0 is the initial time. From initial time, when the time tends to infinity, what will happen to this trajectory? Similarly, when what will happen to the energy of the system when time tends to infinity? So that's what I want to say for this part, that asymptotic stability is the case for unforced system, and asymptotic stability with respect to Lyapunov stability theory is the actually finding out that what will happen to energy when time tends to infinity. So this asymptotic stability, the point asymptotic stability, the initial condition, unforced system, and initial time, okay, and solution of differential equation, these terms are very important to understand Lyapunov stability theory. That's why I'm again highlighting these points with the blue sketch pen. Unforced system, asymptotic stability, initial time, and initial condition, and solution of differential equation. So I will bring these uh, points uh, several times while discussing on Lyapunov stability theory. So that's why before I start the Lyapunov stability theory in detail, I'm just discussing this about these points for your convenience. Now I am starting my today's topic, which is Lyapunov stability theory. Now, in the Google Classroom, I will give you some links from NPTEL website. That is some lectures on Lyapunov stability theory by a professor from IIT Roorkee. Uh, you can also observe this video because these videos are also very good. I will be sharing these links with you tomorrow in tomorrow's session. But I am starting Lyapunov stability theory in more detail. I don't know it is helping for you or not, but I'm giving you I'm entering into this topic in detail. So if you want to skip these details on Lyapunov stability theory, you can open the links from the Google Classroom. Okay. Going to new page. Look at the figure. What I have drawn here, I have drawn a mass spring system. There is no damper, right? There is no damper. A mass is basically is placed on a cart, and it is connected to the fixed surface with the spring of springs constant k, and the mass is having a mass of m. And the friction in the at the wheels with the surface is F. Now I'm going to explain about Lyapunov stability theory. And Lyapunov stability theory, I have said to you already that it is basically based on the concept of energy and asymptotic stability. It triggers the concept of asymptotic stability, and asymptotic stability requires the concept of unforced system. So wherever if you whether you apply your any external input to your system or not, that doesn't matter. If you want to find out the stability using Lyapunov's, you have to consider without any external input. You have to consider the system without any external input. Now, this x is a displacement, right? I've not applied any extra input. That's why there's no force term. Capital F is not here, right? There is no force in Newton, right? To disturb to have this displacement x centimeter. So this is the initial condition. This is already uh, this is already somehow already previously initially there is a displacement without any force. You got I hope that you have get my point. You have got my point that without any force there is a displacement already. That is my initial condition. So this is the case of unforced system I want to say. uh, so this is unforced system and x is the displacement. So x is the displacement. So then what is the differential equation governed by this from coming from the system? Say this is capital M, right? So what is the differential equation? M x double dot plus f x dot plus k x equals to 0. There is no external force, that's why it's 0. It's a unforced system. This is a case of unforced system. Now, what is my state variable in this case? X is displacement, another is velocity x dot. And say the initial condition is also given uh, for this difference. This is a second order differential equation. You see mx double dot. So this is a second order differential equation. And for solving any second order differential equation, you need two initial condition. One is given as x0 equals to 1, and another is x dot 0 equals to 1. 1 1. If you assume your state variable, say let x1 equals to x and x2 equals to x dot. So x1 dot equals to x2 and x double dot means x2 dot plus fx dot means x dot means x2 and x means x1. So from this I can have the individual state equation. And if I am interested to find out the A matrix and B matrix and C matrix, you can also find out. If you can remember, try to remember the theory of state space, where one day I discussed about the solution of homogeneous equation and non-homogeneous equation. And solution of homogeneous equation means that unforced system, and solution of non-homogeneous equation means solution of forced system. And for solution of homogeneous equation is basically, since it is applicable for unforced system, and you can remember that unforced system in state space so what is unforced system in state space? We know that x dot equals to x plus bu, right? X dot equals to x plus bu. Now x dot equals to x plus b, but unforced system there is no input, so only x dot equals to x. So this a I require. So for this example, you need to find out the value of k, a matrix, because this is a case of unforced system. So what is the state equation for homogeneous system? And your initial conditions given for the two state variable, which is 1 1 in this case. Let the values of m equals to 1, f equals to 2, and k equals to 2. So that leads to the new state space equation, which is x1 dot x2 dot equals to 0 1 minus 2 minus 2. So that is x dot equals to ax, and a matrix is in this case 0 1 minus 2 minus 2. Alright. Now if you apply Laplace transform for this equation, what will happen? Taking Laplace transform of the above, it will be s xs minus x0 equals to a xs. And so you take your xs as common, and keep your xs in the left hand side and bring your x0 on the right hand side. So ultimately it will be xs equals to si minus a inverse x0. That you know, that is the solution of homogeneous equation. I already previously I also derived this expression. Now I want to find out what is si minus a, and also you can also find out your si a, because a matrix is available with you. So you find out si minus a, and then take inverse of si minus a. So what is si minus a? And si minus a inverse, you can do it by yourself. I can write down the inverse. It will be s plus 2 by the determinant sign change. So now your equation xs, this is si minus a inverse. So from this equation xs, this matrix is plus 2 with x0, right? X0 is given as 1 1. So if you this is 2 cross 2 and this is 2 cross 1, so ultimately it will lead to you 2 cross 1. So you can check it out by yourself. All right. Now I'm going to find out actually what is my objective. My objective is to have this solution, a differential equation mathematically by taking the advantage of Laplace transform or inverse Laplace transform. Then actually, what is my objective is to find out the solution of this differential equation. The differential equation is given to you already, right? This is the differential equation. Okay. My objective is to find out the solution of the differential equation in time domain, right? In time domain, and then I will explain that how to understand the asymptotic stability from the time domain solution, and then I will bring the concept of energy by considering this same example to explain the Lyapunov stability theory. So that's why I'm actually bringing the concept of solution of homogeneous equation. That's why this is the x dot. I'm solving this unforced system or homogeneous equation for this A matrix. That is, this A matrix is coming from this example, mass spring system. My objective is to find out the solution of the differential equation by applying Laplace or inverse Laplace. So I have that you have already noted the solutions. Let me write this 1 second. Xs is equals to plus 3 by a square plus 2s plus 2 s minus 2 by square plus 2s plus 2. Now this is in the S domain, this is the solution, but this is in the S domain. But I need to find out the solution in time domain. Because time is very important parameter. That's why I have always give stress on the time. In phase plane trajectory also, however time is not seen, but time is actually running. That's why the phase plane trajectory will be moving. So what you have to do now, you have to find out the inverse Laplace of it, so that you can find out x1t and x2t independently, and x1t and x2t are the solution of the mass spring taper system or the differential equation. So you have to do partial fraction for this factor, and you have to do partial fraction for this factor. So let's do it one by one. First I'm taking the x1 solution of the x1 s, that is, and you have to take partial fraction of, since it's a complex, so you break it in complex part and real and imaginary part. So now you have to find out the coefficient a and b. You can follow my steps. So 0.5 minus j. This is for a, and what about b? That will be 0.5 plus j. So therefore s plus 3 by square plus 2s plus 2 is equals to 0.5 plus 0.5 sorry 0.5 minus j by s plus 1 minus j plus 0.5 plus j by s plus 1 plus j. So Laplace inverse, because I need to find out xt, x1t. So ultimately I have to take inverse Laplace. So Laplace inverse of this s plus 3 by s square plus 2s plus 2 will give you 0.5. You can do it by yourself. I'm just directly giving you the inverse Laplace of it. E to the power minus 1 minus j t plus 0.5 plus j e to the power minus 1 plus j t. Similarly, you can also you are also required to find out this inverse Laplace of this part. So you can do it by yourself, or okay, let me do it. Let me do it again. S minus 2, this is s minus 2 by s square plus 2s plus 2 is equals to a dash by s plus 1 minus j. So the denominator is same, so the same partial fraction but different constants, plus b dash by s plus 1 plus j. So similarly you have to find out the value of a dash. Similarly for b dash, similarly you have to find out the Laplace inverse of the second part, solution of the second state variable. You can check it out by yourself. I'm directly writing the solution inverse Laplace of this part. Therefore, the solution of the differential equation, that is Laplace inverse of xs, that was xs and I have found the Laplace inverse of xs already, that will lead to you xt, which is equals to x1t and x2t. xt is a vector and the individual state variables are x1t and x2t in time domain, and we have found that what is x1t, the inverse Laplace of that part, and the inverse Laplace of that part is given here. Let me write once again, 0.5 minus j within first bracket e to the power minus within first bracket 1 minus jt plus 0.5 plus j e to the power minus 1 plus jt. And what about x to t? X to t is the inverse Laplace of that part, lower part of the solution. So this is the this is the part of that lower part. So this must be the expression for this lower part. So it will be 0.5 plus 1.5 j e to the power minus 1 minus jt plus 0.5 minus 1.5 j e to the power 1 plus jt. Now you have to do 2 or 3 steps more for simplification. So you just follow me. This is coming from it. Okay, I'm just breaking this part as e to the power minus t or e to the power jt. All right. So next you to simplify more, I am going to write this exponential term in terms of sine cos. Specifically, this exponential to the power of imaginary power. You can you cannot do with e to the power minus t, but you can do with e to the power jt, because e to the power jt you can break in terms of sine cos term. Okay, let me do it. Now you multiply this factor with this factor, this factor, and this factor into this factor, this factor into this factor, this factor into this factor, and then let's see that what will happen. It will be more. It will be simplified once again. Let me do it. You can do it by yourself in your copy. You can take your e to the power minus t as common. Then inside you multiply. That's why I'm taking e to the power minus t. I'm keeping it out of the bracket, and inside I'm multiplying. But don't worry, I will give you uh, my hand notes in the Google Classroom. If you cannot see what I'm writing here, you can follow my notes also. Now let's check that what are the terms which will be cancelled. 0.5 cos t, 0.5 j sin t plus 0.5 j sin t minus j sin 0.5 j sin t will be cancelled. Minus j cos t plus j cos t will be cancelled. And it's all right. 0.5 cos t plus 0.5 cos t will be only cos t, and sin t plus sin t will be 2 sin t. It's all right. Otherwise, everything otherwise the other terms are cancelled, right? See the below expression. 0.5 j sin t, yes, 0.5 j sin t minus 0.5 j sin t, 1.5 j cos t minus 1.5 j cos t. Now it's all right. So it will be so 0.5 cos t plus 0.5 cos t, it will be cos t plus sin t plus sin t, 2 sin t, and below you have 0.5 cos t plus 0.5 cos t, and minus 1.5 sin t and minus 1.5 sin t, so minus 3 sin t. Now you don't have any j term, and this is the solution in time domain. So let me once again write down the solution in terms of state variable. Now if you decouple this state equation, you can see this is the solution. X1t is equals to this is the solution of the x1t, and x2t is the solution of this. So individually you can write down the solution of the homogeneous system. In this case this is the mass spring damper system. This is the unforced system. Is the case for homogeneous. The differential equation coming of it without input is homogeneous equation. We are solving this differential equation using the concept of state space and Laplace or inverse Laplace. and this is not the graphical solution. This is not the graphical solution. This is the mathematical solution of the differential equation. See, this is the very tedious job. Even you are taking advantage of Laplace, inverse Laplace, but it's still so you know uh, tough to do. I mean, not tough. It's time consuming to do. So, but drawing a phase plane trajectory for this differential equation using method of isocline not so tedious job as compared to this. So that's why phase plane trajectory is popular in such cases. Anyway, so if I write down the solution of the differential equation individually, so these are the solution of the differential equation, and this differential equation is applicable for mass spring system. So, and these are the solution where I have found this solution mathematically. So x1t is a solution of the solution is always in the time domain. So x1t is the first solution, and x2 is the second solution, and x1 is the first state variable, and x2 is the second state variable. Now from the expression of the solution of the state variable, you have to conclude. You can conclude. You observe the solution of the differential equation. See the expression. what will happen when time tends to infinity? Because when I started my lecture today, I initially had given some points to remember, which is initial time, asymptotic stability, solution of the differential equation, and equilibrium point, and so what about time? You can by observing the solution expression of these solutions, x1t is something, x2t is something, uh, can you tell me, can you make your own decision that what will happen to x1t and x2t when time tends to infinity? See the expression is containing e to the power minus t, and it's the x2t solution is also containing the expression e to the power minus t. So when time tends to infinity, what will happen? Obviously x1t and x2t will be 0, isn't it? x1t and x2t will be 0. So what does it mean? It means that, again coming back to the physical system, this physical system, and there is no external input, and due to some initial conditions for x1 x0 equals to 1 and x dot 0 equals to 1, due to initial condition the trajectory will move. That's why you are getting some solutions. But when the time proceeds, when the time is going towards infinity, it will be 0. That means your state variable will be decreased. In this case the state variables are basically displacement and velocity. So ultimately, due to initial condition, due to the spring, due to the presence of the spring, it will oscillate. It will oscillate. Okay, it will oscillate. That's due to this reason. See, the cost and sine term is coming is appearing in the solution. That's why, because initially there will be a oscillation due to the presence of spring, and due to the presence of the spring, the block will oscillate. Okay, and then after some time it will be at standstill. Now whenever it will be at standstill, that means displacement is now 0, and also there's no more displacement and there's no more velocity. So your state variables x1 is displacement and state variable is velocity. X1 and x2 will be 0, and the solution of the differential equation will also give you the same conclusion, that when time tends to infinity, initially there may be oscillation when time is not infinity, but whenever at the initial time or in the transient period there is oscillation. Then after some time, and when the time tends to infinity, the x1t and x2t will go to 0. Okay, the solution will go to 0. So that means that when time tends to infinity, there is the solution will come back to 0. So that is about what will happen when time tends to infinity. When time tends to infinity for unforced system, if such thing happens that when time tends to infinity, the solution will come back to 0, this is called asymptotic stability. Let me tell you once again, when time tends to infinity, if your solution of the differential equation or the state variable will come back to 0, this is called asymptotic stability. So it's not difficult from this expression that the system is asymptotically stable. Now I'm going to relate this concept of asymptotic stability with the concept of energy, and concept of energy is required to establish the theory of Lyapunov's stability technique. So in my next part, I'm going to relate this same example. I'm going to consider the same example, mass spring system. I'm going to consider the same example to explain and establish the Lyapunov stability theory with respect to energy. I'm also going to establish the concept of asymptotic stability in the sense of Lyapunov with respect to the same example, mass spring system. So in my next video, I'm actually in my next video I'm going to relate the concept of energy to conclude on stability and to establish the theory of Lyapunov theory of Lyapunov's. So I'll start my new discussion on this topic in the next video.